About the right level? All right, good. I never know what level to teach at. All right, quick sort. We're going to do it faster, right? Quick sort. You start with the list, and we're going to do divide and conquer. We partition it into two sublists using a random pivot. So we choose some guy to be a random pivot, and then we partition it. Everybody over here is smaller or equal to the pivot. Everybody here is bigger or equal to the pivot, and the pivot's in the middle, right? And then, so actually here's how do we do that split, right? You could write code very similar to the merge, and if you want to get into really annals of it, I have slides on how to do it that I do in 3101 for loop invariance, and I thought I wouldn't do it here, but if you want to do it here, we can do it here too. All right, so we just basically you take your numbers and you put them where they belong, right? All right, so then what does the first friend do? First friend sorts the first half. The second friend sorts the second half, right? Yeah? No. We're going to get into that. It's a randomly selected item. All right? So, all right, so now how do we put the two lists back together? Do we have to merge them? It's one of those. He's definitely right. Well, does it look like we have to do anything? No, they're already sorted, right? The guys over here were started off being smaller than 52, and they're sorted. So we don't have to do anything to stick them back together. Everybody good with that? All right, here's, I made this when I wrote my book. I'm sure you've all bought a copy and gone home and read it. So here we just, we choose a pivot, and you pivot, and I don't know, it's stack frames. So now he was asking, how do we choose what the pivot should be, right? And I was saying choose a random one, but what could you choose instead? You could choose the guy who's in the middle, maybe choose the first one. So here, suppose you just choose the guy who happens to be first in the list. And then what happens if the list that you were given happened to already be sorted, right? You're given a list and you sort it, and then you say, hey, did I sort that? Let me sort it again, right? And the first time it sorts really fast, and the second time not so fast. Well, why? Because here you take, if you pivot with respect to 14, what happens? Right? It doesn't really partition very well. See that? And now you might say, well, it would have been better to pivot with respect to the middle guy, right? But again, on the worst case input, the middle guy wouldn't split very well, right? We're doing worst case inputs. We're assuming the adversary knows our algorithm is coming up with an input. If we're going to pivot with respect to a fixed guy, then you can assume the adversary is going to make that guy be not split very well, right? So let's think about the running time of quicksort. What you want to be doing is choose a pivot that splits it in half, in which case you have this recurrence relation. Everybody remember this? Which the running time is in log n, right? If you split it over there, then one friend isn't given anything, and the other friend is given n minus 1, right? And it took us order n to do it, and that you wind it out, it comes to be n squared time, right? So the worst case running time is n squared. Now I know Andy, when he teaches this, he has a long, complicated proof of proving the running time here. And what we're going to do is we're going to go like this. All right? You ready? All right. So it's going to happen somewhere else. It's not going to happen in the middle. It's not going to happen very often. I mean, once in a while it'll happen in the middle, and once in a while it'll happen at the end. So those bad things or good things will happen, but generally it'll happen sort of there, right, at a thirds or two-thirds, right? So just to give some impression, let's just pretend that at every time it makes a one-third, two-thirds split, right? It's really going to be in a random place, but suppose it does this, right? Now we can sort of analyze what the running time is going to be. So I'm claiming it's still going to be n log n time, and I'm going to prove that to you by waving my hands around. All right, so remember the top level work, it's a list of size n, so the top work is n, right? Then we split it, and actually it doesn't matter where we split it, does it? Because the work this guy is going to do is going to be proportional to his input, and the work this guy is going to be proportional to his input, and their sum is still going to be n, right? So it doesn't matter where you split it, it's going to be n, right? And so every level, no matter where we split, is going to be n, right? Now the question is, how many levels will there be, right? Well, if I go from n to n minus 1, then I'm going to have n levels, right, which is bad. But that's not going to happen very often, right? Normally, the worst side is going to be two-thirds, right? This side is going to be fast, right? But even this two-thirds level, what's the depth of this two-thirds level? Well, it's log of n base 3/2, right, which is the log of, which is order log of n. It's the log of n divided by the log of 3/2, which is just a constant, right? So it comes out to order n log n. Everybody kind of buy that? This is average running time. It might be the next class, but I waved my hand, so you should know it anyway. Now you've got the hands waved. In fact, now that you mention it, I think it was Andy was teaching 3101. He was doing that big, long proof. So come back to 3101, and we'll do it again this fast. Yeah. The log of log base 3/2? Yeah. So log base b for base of n is the log of n over the log of b. Let's just change the base. And here b happens to be 1.5. Oh, I stole these from Andy. That's code. And that's more code. And that's more code. We're good? You can see how I don't like doing it. Right? Yeah, I don't even know. Look at, I don't even, oh, this one's merge. Must be merge sort. Merge sort, merge sort. Quick sort. Okay, merge sort, quick sort. There you have them. So if you wanted to have the code for quick sort, there it is. And if you want us to go over it, study it yourself. And if you want to go over it, talk to somebody else. No, we could go over them if you want. How are people feeling about this code? What kind of answer is that? You're going to get a job in which you're going to have to write code like this. What? Exactly. I think it's just kind of like what we just did, right? It's the same sort of thing. Maybe I should save this for 3101. I don't know. Oh, it's here. Let's do it. Suppose the input is a list and a K. And what you want to do is you want to imagine you sort the list and you return the kth largest value. Right? So here K is 3, so you return 25. Do you understand what the problem is? No? Okay. You're given a list and a K. And here's one way of solving it. You could solve it by sorting the list and returning the kth in the list. So it's returning the kth smallest guy. Right? If K is 1, it returns the smallest. K is 2, it returns the second smallest. If K is n, it returns the biggest. Why? Because that's what our boss gave it to us. And so we return the 25. Right? So the algorithm is you do a random pivot, and then you know you know where you pivoted it, and you now the third biggest is going to be on one side or the other side, and so you recurse on one side or the other side. I think we can skip all this. I don't know. Tell me what you guys want to cover and what you don't want to cover. Here, so the joy here is that you only recurse on one half. You only have one friend, and so the number of friends at each level is still 1. And so, they go down by a factor of 2 each time, right? So it adds up to order n. And so here it's our same list, right? But the number of friends is 1 all the way down, and right, you have 1 friend, so it's 1 all the way down, and so that adds up to order n. Yep. All right, suppose we change the number of friends. So we don't want to go into too much detail, but we split it into 2 lists, and we're only looking for one number, and we know how to know which half it's in. No. We know because if there are 5 elements over here and we're looking for the third, then we know that we're looking for the third on this side, right? But if there are 5 elements on this side and we're looking for the 8th, then we know we need the third on this side, right? Anyway, the point of this exercise is that you only have 1 friend instead of 2, right? And so then the running time, instead of being n log n, becomes only n. And we have this geometric sum that adds up to n. Right? People, good? Here's another little example of you're given a b and an n, and you want to compute b to the n. So what can you do? You can say if b is 0, if n is 0, then you just return 1, right? Because b to the 0 is 1. Otherwise, you recursively compute b to the n over 2 rounded down and b to the n over 2 rounded up, right? Which gives you, and then you multiply the 2 back together. Right? And so here, if you call it on 7, it recurses on those, and it recurses, and they return their values, and we multiply them together. People kind of buy that? Yeah? Oh. In some language, it's a comment. It's a comment. It's just to explain what's going here. Yeah. Instead of a slash. I use percentage. And most of the things I write is LaTeX, and it's a percentage. Everybody see what's happening here? Yeah? No? Right? I'm given a 7, so I divide 7 by 2, and I get either 3 or 4, right? My friends compute b to the 3 and b to the 4, right? And what do? I put 2 back, I multiply the 2, and it gives me b to the 7, right? Does that make sense? Well, that's what we're going to do next, right? So what's the running time, right? You get this whole tree. And I have 2 friends, and each is given half the input. And so you bang it out, and it's going to take you in time, right? You're going to have in base cases, right? But the size of the input, remember I was really big on what the size of the input is, right? The size of the input is only the log of the number of bits to write in and b down. So this running time is actually exponential in the number of bits. Yeah? Yes, that's not bad. That's good. Yeah, exactly. All right, so, but here, look at, we have 2 friends who are almost the same, right? And so that was a waste of time to call them twice, right? So instead, what we're going to do is we're only going to call them once. We're going to divide by 2 and round down, and we're going to recurse once. And then if it's even, we just have to square the value. And if it's odd, we have to bring in an extra b. Right? So let me show you what's happening. If we got 7 there, then we have 1 friend, which is 7 over 2. Our friend gives us b to the 3. And then our answer is going to be b to the 3 squared, which gives us b to the 6. And then we multiply by an extra b to give us our answer. Everybody see that? And now the difference is we only have 1 friend. So, and so it's log capital N, which is linear in the number of bits. All right? Well, do you see why it's log N? Log capital N? Well, it's back to the size of the little n. The size, little n is the number of bits to write down the value. So if the running time is log n and the size is log n, then the running time is linear in the number of bits. Yeah, then you get it wrong. And I've seen that answer many, many times. But let's see the difference here. Here, the time is capital N, and little n is log capital N, right? So capital N is 2 to the size, right? People take pictures. How do you keep track of all those pictures? Oh, it's just a brief moment. All right, that makes sense. I'm like, how do you? All right, everybody see here that the time is capital N, which is 2 to the size, right? The value is 2 to the size, right? But in this case, the time is log capital N, which is equal to the size, right? And that's often running times are linear in the number of bits because we do things like this. Yeah. All right, we're going to, here just slightly, it's almost time for a break? 15 minutes? All right. So here, we talked about this a little bit. If you want to do recurrence, how do you solve recurrence relations, right? And suppose you wanted to find, you have this square of area 36, and you wanted to find the length of one of the sides, right? How do you do it? Is you get a variable for the unknown, right? And then you write down equations that you know about your unknown. Like we know that x squared is 36. And then you guess a value of x, and you plug it in to see if it works. And if it works, you're happy, right? Or if you're better, you can come up with an algorithm for finding x, for solving this. You have an algorithm for square root of 36. Everybody kind of follow that? Right? And that's kind of what we're doing here, right? We're going to guess that the answer is, the running time is t of n, but now t of n is a function. And we're going to write down equations, and then we're going to solve these equations. Right? Is everybody good? So we went through these slides already. I don't think we need to go over them again. You saw all these, right? Towers, so I'm not really sure how much recursion we're supposed to cover here. When in 3101 I asked, what do you guys know? And half of them know Taurus-Hanoi. Half of them know merge sort. We could go on to new material. We could do more recursion.